We often look outwards, to space, thinking that's the big frontier.
Hmm.
But what if the most complex, most mysterious landscape
Yeah.
is actually, well, right inside our heads?
It's a fascinating thought, isn't it? This whole ambitious goal of mapping the human brain, every connection.
Exactly. It's like an inner universe.
It really is, and one that tells us so much about, well, us, what makes us human.
So today on our deep dive, we're venturing right in there. We're going to focus on two really core ideas.
Right. The way the brain seems to have specialized parts for specific jobs,
Localization of function, yeah.
and also how incredibly adaptable it is, how it can change plasticity.
We've got some really great source material to draw on. Studies looking at specific brain areas, but also these incredible human stories.
Cases like HM and Eugene Pauly, people with specific brain injuries that taught us so much.
And then research showing how experience literally shapes the brain. Think rats in different cages, or even London taxi drivers.
And unfortunately also how difficult experiences like trauma can leave their mark.
So our mission really is to piece this together for you, to explore that relationship between the different brain parts and this amazing ability it has to rewire itself.
Think of it as your shortcut, your guide to getting your head around these honestly mind-blowing topics.
Okay, let's start with that first idea, localization of function. The concept that, different bits do different things.
Precisely. And there's no better example to start with than the case of HM.
Ah, HM. His story is foundational, isn't it?
Absolutely. Our sources really detail how studying him after surgery affected his hippocampus was revolutionary.
It showed that the hippocampus was just crucial for transferring information,
Yeah.
right? From short-term memory to, well, long-term storage.
Exactly. He could hold on to things for a few moments, but then, poof, gone. Couldn't form new lasting memories of events or facts.
So that pointed strongly to a very specific job for the hippocampus, memory consolidation.
It did. But, and this is key, while parts have specific roles, the brain almost never works in isolation, especially for something complex like memory. Ah, right. So it's not just one spot.
No, it's much more like distributed processing. Think of it as a network. Multiple areas lighting up and working together.
A team effort, kind of. Different regions coordinating to make or recall a memory.
That's a great way to put it. Memory isn't just filed away in one little box. It's spread out. It involves collaboration across regions.
Which I guess is where things like the Human Connectome Project come in.
Exactly. Our
Yeah.
source mentioned that. This huge effort to map all the connections, all the neural pathways.
It's like mapping every single road in a massive, complex city.
Pretty much. Understanding those connections is fundamental to understanding how the brain actually does what it does. Thoughts, actions, everything.
Okay, so let's talk about some of those key areas the sources outline. We have the brainstem.
Right. Handling the absolute basics, breathing, heart rate, things we don't consciously think about. Psychologists don't usually focus there as much.
And the cerebellum,
Hmm.
often linked to balance, coordination.
Yes, but also, interestingly, involved in aspects of speech and even classical conditioning learning associations. Huh. See? Already more complex than you might think.
It really is. But the main player, especially in psychology, is the cerebrum, the big wrinkly part.
Divided into the four lobes. Okay, let's quickly run through them. Frontal lobe.
That's your executive control center, like you said before. Planning, making decisions, problem solving, even producing speech, higher level stuff.
Got it. Then occipital lobe at the back.
All about vision, processing what you see.
Parietal lobe, kind of top and side.
That deals with sensory input, touch, temperature, pain, perceiving stimuli from your body and the world.
And finally, temporal lobe, near the temples.
Crucial for hearing, understanding language, and importantly for our discussion, heavily involved in memory.
Okay, now within all that, there's this network called the limbic system, often called the emotional brain.
That's right. And it's deeply interconnected with both emotion and memory. Really crucial stuff. Our sources break down the key parts.
Let's hear them.
Okay, first, the amygdala. Think emotional memory, especially fear. It flags things as important, emotionally significant.
That makes sense. Those flashbulb memories, often tied to strong emotions. The amygdala is working overtime.
Pretty much. Then you have the basal ganglia. These are really interesting, key for habit formation.
Procedural memory, like learning to ride a bike or type. Things that become automatic.
Exactly. Those ingrained motor skills and habits. We'll come back to those.
Okay. Then the hippocampus, which we've already touched on.
Yep. The gateway for forming new conscious long-term memories, facts and events.
And the hypothalamus.
Yeah.
Small but mighty.
Incredibly mighty. It's regulating so much: body temperature, hunger, thirst, sleep cycles, maintaining homeostasis. Plus, roles in emotion, controlling the autonomic nervous system, the pituitary gland. It's a major control hub.
Wow. Okay. And one more.
The nucleus accumbens. This one's strongly linked to reward, motivation, pleasure, and unfortunately, addiction. That drive to repeat rewarding behaviors.
So this whole limbic system is this complex interplay of structures driving emotions, motivation, and locking down certain types of memories.
Precisely. And to really hammer home that distinction in memory types, let's talk about Eugene Pauly, EP.
Hi, yes, EP. His case is fascinating because it contrasts so well with HM, doesn't it?
It really does. EP also had brain damage caused by viral encephalitis. But crucially, it wiped out both his amygdala and his hippocampus.
So, like HM, he couldn't form new conscious memories.
Correct. He couldn't consciously recall new facts or events. For example, he couldn't draw you a map of his own house, even though he'd lived there for years post-illness.
But, and this is the amazing part, he could still find his way around his house, right? Like get up and walk to the bathroom.
Exactly. That's the kicker. How could he navigate without a conscious map in his head?
It must be a different kind of memory.
Precisely. It highlights the difference between cognitive memory tasks, knowing that something is the case, which relies on the hippocampus, and associative or procedural memory tasks, knowing how to do something. Habits.
Like driving a car. At first, it's all conscious effort.
Totally. Your frontal lobe is working hard. Clutch, mirror, signal, gas. Very deliberate.
But eventually it becomes automatic.
Right. And as it becomes a habit, the brain cleverly shifts control. More involvement from the basal ganglia, which, remember, are intact in EP.
So for EP, walking to the bathroom was a deeply ingrained habit, stored in his basal ganglia, even though the conscious memory circuit involving the hippocampus was broken.
That's the idea. It became procedural. He could even go for walks around his block following a specific route he'd done hundreds of times.
But didn't he get lost if something changed?
Yes. If his routine was disrupted, like, say, construction blocked his usual path, he was completely lost. He didn't have that flexible cognitive map stored via the hippocampus to figure out an alternative route.
Wow. That really drives home the difference between habit-based knowing how and conscious knowing that.
And the researchers used multiple methods, didn't they? Not just talking to him.
Right. Our source mentions interviews, psychometric tests like IQ tests, careful observation of his behavior.
And crucially, MRI scans. Those scans confirm the specific damage, amygdala and hippocampus gone, but basal ganglia relatively spared. It provided the physical evidence linking structure to function.
That ability of the brain to rely on different systems or find workarounds leads us perfectly into the next big topic, brain plasticity.
Ah, yes. The brain's amazing capacity to change. It's not static hardware at all.
It constantly adapts throughout life.
Absolutely. Plasticity just refers to the brain's ability to modify its own structure and function in response to experience, learning, or even injury.
And this happens at the level of connections between neurons, synaptic plasticity.
That's a key mechanism. When we learn the connections, the synapses between neurons can strengthen or weaken, new connections can form.
Our source mentioned dendritic branching, like tree branches growing.
Exactly. Dendrites are the input receivers on a neuron. When you learn something new and practice it, those dendrites can actually sprout new branches, forming more connections with other neurons. The physical wiring changes.
And there were those early animal studies? The rats?
Yes, Rosenzweig, Bennett, and Diamond back in the 70s. Classic studies. They put rats in different environments.
Some got the enriched environment, lots of toys, other rats, things to explore.
While others were in a deprived condition. Basically isolated, nothing much to do.
And the brains were physically different.
Significantly so. The rats from the enriched environment had a thicker cerebral cortex, the outer layer involved in complex thought, and, importantly, more dendritic branching. Their frontal lobes were even heavier.
That's incredible. It really shows that stimulation and learning physically build a better brain, doesn't it?
It strongly implies that, yes, the importance of an engaging environment makes you think, doesn't it?
Definitely. And it's not just rats. The London taxi driver study is a fantastic human example.
Ah, the Maguire study. Yes, learning the knowledge.
That insanely complex map of London streets they have to memorize. Years of training.
A massive spatial navigation and memory task. So Maguire's team used MRI scans to look at their brains compared to a control group.
And they found differences in the hippocampus, right? the area we know is crucial for spatial memory.
They did. Specifically, the posterior part of the hippocampus, the back part, was significantly larger in the taxi drivers.
While the anterior, the front part, was smaller.
Yes. And even more compelling, there was a correlation. The longer someone had been driving a taxi, the larger their right posterior hippocampus tended to be.
So the brain was physically changing in response to the demands of the job, adapting.
It really looks that way. The hippocampus seemed to reorganize itself, dedicating more neural real estate to spatial navigation because it was used so intensely. It got a workout like a muscle.
That's a great analogy. But plasticity isn't always positive, is it? The sources mention stress.
Right. Chronic stress can actually have detrimental effects, particularly on the hippocampus and memory. There's research from abnormal and developmental psychology on this.
And the Bremner study, looking at women with PTSD related to childhood abuse.
Yes. A sobering example. Using MRI and PT scans, they found that women with abuse histories and PTSD had, on average, smaller hippocampal volumes.
And their hippocampi were less active during memory tasks.
Correct. It suggests that severe prolonged stress can actually damage or impair this crucial memory structure. So experience shapes the brain, for better or for worse.
It really underscores how interconnected our experiences, emotions, and brain structure are. So let's get down to the nuts and bolts. Synaptic plasticity. How does that work biologically? The use it or lose it idea.
Right. At its core, it's about strengthening connections that are used frequently. This is called long-term potentiation, or LTP.
LTP.
Think of it like this. If one neuron repeatedly stimulates another neuron across a synapse, that connection becomes more sensitive, more efficient. The signal gets through more easily next time.
Like forging a path on the grass by walking it over and over.
Exactly. And this isn't just a temporary boost. LTP can lead to lasting changes. It can trigger protein synthesis, changes in which genes are expressed.
Which ultimately leads to physical growth. At dendritic branching or neural arborization.
Yes. The neuron physically remodels itself to strengthen that connection based on repeated use. Learning changes the brain's microwiring.
But it's not just about building. There's also pruning, getting rid of connections.
Absolutely crucial. Synaptic pruning. The brain eliminates synapses that aren't used much or aren't effective.
Why would it do that?
Efficiency, mostly. It's thought to streamline the neural networks, making the remaining important connections work better, like cleaning out clutter to make things run smoothly, pruning the weak branches so the strong ones thrive.
Okay, so let's try and pull this all together from our deep dive. The brain is, well, incredibly complex.
Definitely. It has specialized areas, localization of function like the hippocampus for certain memory types.
But these areas don't work alone. They're part of vast distributed networks, especially for things like memory.
Right. And maybe the most remarkable thing is its plasticity, its ability to change its own structure and function based on what we do, what we learn, what we experience.
From learning a new skill, strengthening synapses through LTP and growing dendrites,
To the brain adapting to intense demands like navigating London, or sadly being affected by stress and trauma. And we saw that clear difference between conscious memory and ingrained procedural habits thanks to cases like EP.
So understanding these core ideas, localization, distributed networks, plasticity, different memory systems, gives you a really solid foundation.
Absolutely. A framework for thinking about how we learn, how we remember, how we adapt.
So here's something to maybe reflect on. As you go about your life, think about your own environment, the stimulation you get, the things you're learning, maybe even the routines you follow.
How might all of that be subtly sculpting your brain right now, every single day?
What does that constant ongoing neural remodeling mean for how we live, how we continue to learn, and how we face challenges?
It's a pretty profound thought. Maybe that inner frontier, the one inside our skulls, really is the most dynamic and fascinating one of all.